All right, everyone, it is now 3:30, which means it is time for us to get started. Welcome back to another lecture of Comp 426, Modern Web Programming. This is lecture 7. To give everyone a chance to settle down so that we can go over some announcements. Right? Okay. All right. So to get started here, again, A02 Pixel Art Maker, that is due tonight at 11:59. A lot of people already started. They've been coming to office hours, so it's been looking really good. Of course, also on there, just as a note, like usual, we have a late due date, usually 2 days later. So if you need extra time, you're free to use it. And then secondly, our first midterm is going to be on Thursday, so 2 days from now. Today's content, and I'm jumping a little bit ahead, so the last content that was going to be on the midterm was on Thursday with asynchronous programming. There are 2 more slides that we'll be going over that extend that lecture, so those will be included. And then all the rest of the content will not necessarily be included, but it will show up as extra credit questions. So that might be a way to, improve your grade if you forget something else. Okay. Now remember that details for the midterm have been posted on the website. So if you go to the website under the schedule, there is a listing for midterm 1. And then next to that particular listing, there is a button that says details. And you can press on that, and then there's going to be more details about the midterm there. In addition to that, so we have the types of questions that will be on there, the different types of content that will be on there in terms of all the different sections, some practice questions, and also a guide that kind of goes over and summarizes the key points from all of the different lectures. Okay, so we'll also have some time, hopefully at the end of class, to go over it a little bit more in depth. All right, any questions here? Great. All right, so there's 2 announcements that I would like to share. So the first one is that our amazing career services team here in the department is hosting a career fair that's lasting 2 days. So it starts today, and then there's another one tomorrow. So tonight, this is night 1. It's from 6 to 8:30. It's virtual. So definitely feel free to check that out. In addition, the second night is in person at the student union. It is also, so it looks like here, 6 to 9 p.m. So I highly recommend. There's some QR codes there for some information. So this is a great opportunity. The career team always does a great job with hosting these events. There are a lot of different companies coming out. And I know that recruiting season is probably underway right now. So if you're interested in, or you're trying to look at different job opportunities over the summer and maybe full-time roles, this would be a great chance to kind of get more prepared with that, ask around, talk to some people in industry, and overall learn more about software engineering in the real world. All right, any questions here? All right, and then for the next announcement, I have the honor of introducing Alicia to talk a little bit more about Hack NC. Should be on.
But it also made sense a great opportunity to private time resume, get a team together, and demonstrate your proficiencies on tech stacks, or and also talk to some recruiters. So we'll have a sponsorship there. We'll have free food, merch, workshops. So hope to see everyone there. Again, this QR code is to register, and we also have go.unc.edu/SNC2025. Thank you.
All right, thank you, Alicia. Thank you. All right, so again, here, Hack NC, highly recommend registering. I participated last year. It was great. There's always great prizes, great chances to meet people, work on some cool projects, and it's usually one of the most festive times of the year in our department. So again, highly recommend registering for that. All details, again, will be available on the slides. They should be up. So if you want to click any of these links and register, you are free to do so. All right, so with that, that finishes up our announcements. So this is kind of where we left off last lecture. There's just 2 more pieces of content that I think will be important to go over and that we could have gotten to, but we ran out of time. So again, we talked a little bit about asynchronous programming, the fact that we can mark functions as asynchronous, and this implements asynchrony using these things called promises, right? So whenever we mark a function as async, the return type, instead of just being that value, it is a promise or a shell, essentially, that is basically saying that there might not be a value right now because the operation takes a long time to run, but at some point in the future, we will get some value back. So that is a promise, and then promise-based asynchrony, that is kind of what we looked at on Thursday. Any questions there? All right. There's also one other way that asynchrony is implemented, and this is called callbacks. So we talk about promise-based asynchrony. That's with our asynchronous functions. That's with fetch. All of those things use promise-based asynchrony. But callback-based asynchrony is kind of a similar idea in the sense that we have a function that we want to run in the future after some asynchronous process ends. The difference here, though, is that we pass that function in directly into our asynchronous call. So an example here is with this set timeout. This is kind of the main example that we use for callback-based asynchrony. And most of the time when you see this type of asynchrony, it's usually with some built-in function built into our programs, right? So set timeout, that is available. We'll actually we'll hear more about this today in lecture, but this is made available. You can call it from your code. You didn't have to make it, it's built in, right? And so you can see here the way that this works is, and I boxed it here, we pass in a function as the first parameter, and we say in the second parameter some duration in milliseconds. And so we're saying that after 1,000 milliseconds, we want to run this function. Okay? So the main difference here between callback-based and promise-based, right, is that by doing a promise, you would have to call the function, then write .then, right, and pass in a function. With callback-based asynchrony, that is kind of abstracted away. All you have to do is just pass in a function, and the browser and kind of JavaScript itself will handle the rest in terms of getting all of it set up. And it works in a very similar way, where in this case, 1,000 seconds in the future, that function is going to run. Any questions here? All right. So the key thing here, and this actually may have come up if I remember correctly in the practice problems where you may have seen set timeout. So I do apologize that we weren't able to get to it. So if you saw that and were a bit confused, it's here now. So really the only type of question that might be associated with this, you might be asked, does this line implement callback-based asynchrony or promise-based asynchrony, right? And so if you see set timeout, you know it's callback-based. And if you see fetch or an async function or anything else, then it's promise-based asynchrony. All right, any questions there? Perfect. All right, so I have one more slide here just to show some examples of both. So again, we had our promise-based asynchrony here where we called like dog and then we write .then. That's a promise. Here, we just use set timeout. We pass in a function and it will run in the future. All right, so this is just a bit of a visual representation of the differences here. All right. So now this is the start now officially. So that's the end of the content that is mainly focused on midterm. This is the start of our last piece of our foundations module or fundamentals module. And I think that today we'll really begin to tie up the loose ends, all of the different things we talked about, things like event handlers, things like the DOM, asynchrony, higher order functions, everything will come together today as we kind of introduce browsers and what actually makes up a browser. So you actually see how these pieces interact and how they actually work a bit under the hood. And this is foundational to kind of understanding how web applications work because, of course, all of our web applications run in a browser, right? So again, here you can see browser, a definition is on the screen. So it's an application used, right, to retrieve and to display information from the internet, right? So we can go to a website, it gives back some HTML, and our browser displays that nicely to us on our screen. Or for example, you can, like we did in last lecture, we can fetch to some API endpoint and get some data back. And so our browser is just responsible for retrieving data and then displaying some data. And there's many different types of browsers. These are some of the most popular ones, right? Chrome. If you're on Mac, you use Safari, maybe Microsoft Edge. There's Firefox and Opera, and there's many different types of browsers. I know Arc and some other ones were popular. Seen some people use those. So these are all different types of browsers. Yeah. And so these are kind of the main browsers that dominate the industry, what majority of people use. I believe that Google Chrome is so large, it's used by like millions and millions, it might even be a billion devices. I don't remember the exact number, but it's a huge part of the market. In fact, I think something, if you've been caught up with recent events, I think there was some news about Google and Chrome and whether or not the influence of Chrome is so great that there's some anti-competitive practices going on. So I don't remember the exact result of that, but again, Chrome is huge, and so that was in the news. Right. But it's important to note here that these are all different browsers. They're made by different companies, right? Chrome by Google, Safari is Apple, Firefox is Mozilla, and et cetera. And so all of these browsers differ a little bit. Right? So all of these browsers are not necessarily exactly the same, and some of the features that they support may also differ depending on the implementation of the browser. Right? So many documentation websites that you'll see for things like HTML or CSS will often mention something called browser compatibility, and whether or not, right, different elements or different CSS features are supported by all of the different browsers. Right? So for example, here are two that I have here. These are, I believe, both CSS. Right? So padding, for example, that's one CSS style rule. And of course, padding is very widely supported. Right? So you can click on this, and this takes me to this documentation here from Mozilla, and you can see that padding is widely available on most of our browsers. Right? It's something that's used pretty much in every website, with styling at least. And I lost my, there we go. Meanwhile, though, something like Speak As, so if I click on this, right, you can see that Speak As is a CSS property. You can see it says it's used to determine how HTML content is spoken. Right? That is not widely available. So you can see it's supported by Safari, but it's not supported by Google Chrome, by Edge, or by Firefox. Right? So even though CSS is kind of this one, we say it's a language, it's a way that we can specify rules for styling, well, the browser ultimately is responsible for taking that CSS and actually doing something with it, right? Padding, it actually shows on the screen that an object moves. And there are some cases where CSS might evolve, but the browser might not support it yet. So it's important to note that as you move forward and you use different features, that especially if you're using ones that are not widely supported, that you are made aware of that. Okay? Go back here. And so again, as I noted, it's when in developing websites, it's important to make sure that the tools and the different pieces that you're using are supported by different browsers so that your app works on most of the browsers, right? If I had an app that really relied on that Speak As CSS property, well, a good majority of browsers, it would not work on it. So it's important to know. Okay. And so a browser now, we've said that the browser is responsible, right, for getting a website, for showing it. But what are the different pieces of a browser? What actually makes it up? Right? So there are many different essential kind of components inside of a browser that most browsers have that power its features. For example, the first one might be something like the rendering engine. So the rendering engine is responsible for taking the DOM, right, which is some data representation of our website, and actually displaying something on the screen to the user, right? It renders our web page so that you can see it visually on the screen. Right? So the browser is what's responsible for taking the DOM, which is this data representation of our website, and actually displaying it. And that's one piece of our browser. You also, most browsers have like a networking service, which is responsible for actually making the network requests, right? Your browser makes a request to a server. How does it actually do that? That's some functionality that's built into the browser. And so there is some functionality specified in the browser for that to happen. Other things, so storage, we haven't talked about that yet. We'll talk about that in a little bit. I/O, input output, right? If you have a camera or you have a microphone input that you're using in your app, maybe you're on Zoom, right? A Zoom website, and you're trying to use the camera and use the mic to talk to somebody. These are features built into the browser. Each browser might implement this in a little bit of a different way, but typically all browsers include this, right? And then the last piece of the puzzle here is this abstract piece that we're calling the JavaScript runtime. This is the actual functionality in terms of what actually runs our JavaScript code. Right, so this is our running JavaScript. When we take a JavaScript file and we run it, the JavaScript runtime is responsible for actually running this script that we download. Any questions so far? All right. So what we're going to do now is we're going to round out this module by kind of talking about this runtime, because it is the battery. It's like the engine of everything that we have been talking about and working with. The JavaScript runtime is responsible for. Okay, so it's a very important piece to this puzzle that actually makes the web work and make websites function. So and it's slightly unfortunate here that my colors compared to the slides, if you actually download the slides, there's like a gray border. But for some reason, I think due to the lighting in this classroom, the gray is so faint that it's very hard to see. But you'll see it if you download it. I'll also just very quickly show you where my, whoops, I think I refreshed my page by accident, where these boxes are. So like I have a box here for JavaScript runtime, and then I have like another box here for all my actual different engines and features within the browser. Right, so you can kind of imagine here that as we build up our diagram, we're going to have separate sections for each of these things. Okay? And so our browser contains both of these. So the first thing that we're going to add here into our JavaScript runtime is the stack and the heap. Right? We have talked about the stack and the heap a lot. You have talked about it in Python maybe. And now we talked about it in our lecture with higher order functions, with functional programming. And so the stack and the heap, right, are essential to us running JavaScript. As we run functions, right, we add some frame to our call stack. We add some different functions, right, into our heap and store it, etc. So the call stack and the heap are a very important part of our JavaScript runtime. Right? So again, if you remember back, right, these memory diagrams, you were diagramming out a part of the JavaScript runtime when you were doing so. Right? So I know memory diagrams are not the most fun thing in the world, but you can kind of see the connection to why that is important. And even though when we run our programs, we don't really think about the stack and the heap, they're still there, and that's what's powering everything that we're doing. Right? So now what I would like us to do is to explore what happens when you actually load a web page in relation to our diagram here, right? So the first thing that happens, I use apple.com a lot. Maybe we'll use google.com today just to balance things out, right? So let's say that we load google.com. Well, our networking service is going to it's going to first talk to DNS, find what IP address to contact. Then it'll contact some server, say, give me the HTML file for this website. That's step one. Right? So we get some HTML file from the networking service. We download that into our browser. Then remember the two kind of pieces of our HTML file, right? We start off with that head section, which is our metadata. Right? So in that metadata section, we include things like the title of the website, but also links for references to our style sheet, like where is our CSS file or some JavaScript file, right? We link to those things in that head section of the HTML. And so our browser will see that, and then it will make another request to our server for those files as we need them. So it will request our CSS file, and it will also request our JavaScript file. So you can see ultimately that we get all of these files directly here downloaded to our site. And maybe also as part of this diagram, right, a rendering engine might render what HTML is being shown. Okay? But let's just focus here on the JavaScript piece. So we have some JavaScript file that we've downloaded. What happens? Right? Well, we're going to execute that script from top to bottom. Right? Remember back in the last few lectures, say that when you get a JavaScript file, it's a script. We run it top to bottom, and that's what we start out with. So we have a script. And the first thing, right, is when we start running our script, a global stack frame is created because this is our global scope for our program. And then we begin executing our code. Maybe in our code, we call some function, right? So we push another frame onto our stack. Maybe in that function, we create some object on the heap, right? Maybe we call another function, create another object. And then as we are finishing our program, right, we start popping off of the stack. So that function frame is popped, my func is popped. And then finally, one thing to note here that's very important is the global frame actually does not get popped when we're done executing. It just changes state to idle. The reason why we do that is because of global variables, right? So maybe there is some global variable we create in our program that we want to make sure still exists. If, for example, an event handler is run, maybe we rely on some global variable. If we got rid of the global stack frame, then all of our global variables are gone, and things would not, like closures, all those type of things would not be possible if we don't have, if we have no frames left. A good example of this, and I can see actually here if I pull this up, because I might still have it, and actually go to our 25F, and let's go to the event handling example here, because I believe there was a code example somewhere in here, this one. And I do hope that there's something still in here and that it's not blank. If it's blank, I'll be a little bit sad. Is it blank? Okay, it's blank. So let me see if I can sign in here real quick and show us our thing here. So let me sign in. There we go. We're logged in here. And let's try and find our example if we have it. If we don't have it, that's okay, but I wanted to, there we go. Okay, we have it. So we're back. Okay, here we are. So this was the example that we talked about in that lecture. And you'll notice that what we had was we had some counter and we were increasing that counter, right, as we pressed this button. So we said increment counter, and as we pressed it, the counter increased, right? But that counter variable, you can see here, is defined in our global scope, right? So if we popped that global frame off of the stack, then we would never be able to increment the counter later on like we do here whenever we press our button. Okay, so that's the reason why we do not get rid of that global stack frame. It's still there. We mark it with idle to say our program's done running, but it still exists so that our variables and our values can remain. Any questions there? All right. Let's go back. Fortunately, I might have to do some animations again, so let's go through those. There we go. So that is those are kind of the two core starting components of our runtime, the stack and the heap. But there's more. So let's kind of think about the different tools that we've used and begin to build this up. So the next piece that we're going to add here to our runtime is called Web APIs. Okay? And Web APIs, you can see here, they serve as our interface between the browser features, which are over here, like our rendering engine or the network service, and the code that we actually execute. Right? So you can kind of think of Web APIs here as the bridge between these things. And so what I'd like you to think about now for the next 2 minutes or so is to think back to the different examples that we've thought about. And what are maybe some objects or some functions that we have used in JavaScript or TypeScript that allows us to interact with these features? For example, rendering engine, networking, etc. So spend around 2 minutes on this, and then we'll come back and talk about it. All right, everyone, let's come back together. Does anyone have any thoughts or would like to volunteer maybe something that you all talked about or discussed? Yeah. Mm-hmm. Like the event handling? Yeah, exactly. May I expand further? Do you remember the name of the object or function that you use to do that? Add event listener, exactly. So add event listener is an example that interacts with our rendering engine because it's connecting some JavaScript or some TypeScript functionality to an item or a node in our DOM tree. Perfect. Any other thoughts? Yeah. Exactly. Yeah. I actually don't even remember. Was that alert? Was the alert? Perfect. So yeah, I completely forgot about that one. That's a great example as well. So that is connecting our browser to code where we can call a function and then show up a pop-up. Perfect. Any others? Yeah. Exactly. Yeah. So the color picker, getting the colors out of there, I believe also might fall into the DOM, but there might be another function. So exactly. Any others? Particularly a hint, we talked about the rendering engine a lot, but what about the networking service? Yeah, fetch, exactly, right? So we use fetch to make requests, and that connects our code to our networking service. Perfect. Those are kind of the main examples I was going for. So great work, right? So again, document is the one that we use to access the DOM. So typically you write something like document.getElement by ID, and then element.add event listener. That is all part of this document object. So that is a web API. And that helps us to connect our JavaScript code to the rendering engine. Fetch, other perfect one, right? The ability to utilize the networking service to make requests, make requests on HTTP to get some result back from the server. Console is another one. So whenever you write console.log, right, you end up printing something into the console of the browser. That is a browser functionality. So there is this built-in API that allows us to log or write errors, etc. And then again, alert I know is not up here, but that's a great example. So there are many, many, many more. And there's actually a list of them, which you can see. I'll also give a bit of a hint here. Set timeout is another one. So a lot of these, in the last few lectures, when I've kind of been referring to these things as quote unquote built into JavaScript, right? I've been using that terminology. What I mean by that is actually these are web APIs. So they're part of the JavaScript runtime, but they allow us to interact with our browser. And so again, if I click on this link here, there's many different options. As you can see, there's a big list. Things like Bluetooth, for example. Battery status is one. I think, so console, right? We talked about that one. The DOM, right? Document object model. All these different pieces, these are all web APIs. Fetch, for example. Any questions? Perfect. So it's important to note here that web APIs are actually implemented by each browser individually, right? This is important to note because, again, we talked about the fact that we have all these different types of browsers. When I say, right, we have all these different browsers, Chrome, Safari, Firefox, they're all made by different companies, and they might have very different implementations for how the actual pieces under the hood work, like the net rendering engine or how it makes requests. There might be some differences there. And so the browser supplies the JavaScript runtime with these web APIs. So they are implemented individually by each browser so that, and they're all kind of conforming to the same standard. So we can use them in our JavaScript code. And then depending on what browser we're running it on, it will run the correct functionality. Any questions here? All right. So now we're going to expand on the first one, which is our document web API, and kind of begin to think about, well, how do event handlers then actually work, right? We say that we add some event listener, and then when you press, maybe let's say you press a button, we run some function. How does it work in this diagram? So you can imagine here, again, let's just say I got some JavaScript file, maybe from google.com, right? We start executing our script. So we will put our globals frame in there. Maybe we call some function. And then maybe from within this function has some code to add an event handler, add some event handler to, let's say, some button on our website. Right? So let's say in particular that we have some function fn where I've kind of added this just to my heap, just as an example. So I have this function. I've given it some arbitrary ID like 1. And we want to say that, well, when some button is pressed on our website, we want this function to run. So what happens here is we will use the document web API. So you can see here, the first thing we typically do is we get the element. So we say document. So that's our reference to the DOM. Document.getElement by ID. We get our element. And then we say element.addEventListener. And let's say that the event that's listening to is click, and then I pass in my function in there. I've kind of, there's nothing, no functionality in there. It's just kind of a shell, but you can imagine there's some function here that we're trying to connect. Right, so what happens then is when we make this call, .addEventListener, we will register with the web API this connection between a node in our DOM tree. So you can imagine maybe this right here is my button, right? So maybe this is some plus button, and this is the button that is I'm kind of referencing with this green dot. And I'm saying that when I press this button, I want this function to run. Right? So it's creating this association between an action on this element and some code actually running. Right? Jumped ahead of my blur, my little pop-up here. So again, right, we register that event handler. And then we get to a point where our script is done running, right? We ran our script top to bottom. We've set up our event handler. And now our globals frame is idle, meaning there's nothing currently running. And now we're just sitting there waiting for the user to interact with our website or our button, right? And so what I would like you to think about now for, again, a few minutes is when this button is pressed, do you think that the document API adds a stack frame for this function and right, directly onto our stack? Is that OK to do? Right? Because remember, we talked about the fact that when you call functions, right, you create a new stack frame. Is this good to do? Is this safe to do? Do you think there are any problems with this that might come up? So think about this for around 1 to 2 minutes, then we'll talk about it together. All right, everyone. So any thoughts here? I guess we'll start this off with just a kind of a semi-anonymous poll. Don't worry, I won't look at your faces. I'll just look at the hands. Anyone who thinks yes, raise your hand. OK. And then what about no? All right. So that seemed, from my point of view, pretty even here. So let's talk about that. So it might seem, so my arrow here is just me pressing this button as an example. So I press this button, and let's continue on. So it might seem in this case that I can just run my function. I can add a stack frame directly onto my stack, and I can run it. And it seems OK, because right now my global stack frame is idle. Right? There's nothing that's currently executing on my call stack, right? But what if something else is already in the process of executing, right? Let's say that we're running some code or a script is still running, and we press that button really fast, and we press that button while something is still going on, right? So let's say in this case, I'm running this function something else, and I press this button. Well, if we just allow our document web API to immediately add this function's call stack frame directly onto our call stack, right? Well, we risk this thing of basically stepping over an already existing process, right? We cannot interrupt if some process is currently executing, like in this case, my something else function. We can't interrupt it by, while it's executing, to just immediately start a new process and add a new stack frame onto our stack. Right, so that's very important to note here. So in my original diagram here, it does seem fine because we're in an idle state. But you could imagine that if there is something running, then this would be an issue. And so I'd like you to think now back to one of your, I'm sure, favorite courses, Com210. What data structure in Com210 do you usually use to essentially keep things waiting in line, a first in, first out data structure? Louder? Queue, exactly, perfect. So this is one of those situations where, again, you may have been wondering in your computer science career why data structures is taught so early. It's because data structures gives us a bunch of tools to solve problems. And maybe you've just been implementing this. Maybe you were asked to make a cube. You may have not seen a reasonable application for one. But in this case, you can actually see where a queue is going to be needed, right? So again, queue. So what we do here is we add another item. And again, my boxes here, it's a little bit unfortunate. So what I'm going to try to do, at least for this diagram, is you can kind of see where these are. I'm going to make these darker just for this particular slide so you have a conceptual idea of where these things are. There we go. So you can see that we add another item into our runtime called the task queue. The entire job of the task queue is to essentially keep processes in line so that if there is some current process executing, we can essentially just say that, well, we want to run that function because we need to run this event handler. Let's put it in line. And once there's available space, then we can go ahead and run it. Okay. So instead of pushing directly onto our call stack, whenever we call one of these web APIs, like a event handler, it's going to add our function call into the task queue, not directly into our call stack. Do you have an understanding on why this exists? Perfect. Again, we don't want to interrupt an already existing process, right? So this function call will be lined up. It'll be queued up. It'll be ready to go so that when the call stack is empty, when we're not currently executing something, then we can go ahead and execute it, right? So in this case, once my something else frame is done running and my global stack frame becomes idle again, meaning we're not running anything, at that point, we can then go ahead and execute that function. That way, we're not interrupting any existing processes, right? And so again, once the call stack is empty, it's time to run our waiting task. And so the next piece of our runtime is the event loop. And so the event loop's job is just responsible for taking something from the task queue and adding it onto the call stack whenever it is ready to be executed, right? So the event loop is just going to constantly check our stack. If the stack has some process on it, we're going to wait. Once the stack is ready to go, once there's nothing else currently executing, it's then going to take any waiting tasks from the task queue and push it onto our call stack, right? So it'll dequeue the item off of our task queue and put it onto the call stack, right? So this allows us to essentially work with the fact, again, that we have one call stack. This is a single threaded, right? JavaScript is single threaded. And so we can only have one thing executing at a time. And this is our way of managing that. Any questions so far? Yeah.
There's only one frame outside of globals that's on the call stack.
So I'll add on to that. So I think what the event loop does is it will only, like if there is only one, so there can be multiple frames, right, on the call stack, because this function, for example, might call another function, and so we can keep adding to it. But what the event loop will do is just say that as long as there is something above, like there's some stack frame that's currently executing, whether that be globals or anything else, we wait. And then immediately, once there is no frame above globals and globals is idle, where it's not executing anything, that is when the event loop will kick in. Any other questions? Yeah. Exactly. Yeah. So great question from the front in case you couldn't hear it, right? Sometimes you load a website, you press something, doesn't do anything for a little bit, and then like there's a little bit of a delay and things are loading. This might be the reason why, because the call stack is running a bunch of things, setting up things. It hasn't gotten to your event handler yet. Exactly. Yep. That's why we're talking about this today, because again, this kind of helps to connect different things that we talk about and help understand why things work. So great question. Any other questions? All right. So now our event handler function executes, right? Once we move it onto the call stack, and it pops off the stack when it's done, right? So that is essentially how event handlers work. Event handlers, again, paired with, so we use the document web API, we have a task queue, and this is what manages all of our functionality. Now let's round this out by talking a little bit about what we were talking about last week, asynchronous programming, right? It may have been because I used this terminology on Thursday where I kind of said that we start some asynchronous process, we let the browser handle it, right, on the side, and then once it's done, we then do something with the result. Right? Because JavaScript is single-threaded, it can only execute one thing at a time. And so we'll actually see now with these different pieces how asynchronous programming is able to be done in a single-threaded context like JavaScript, right? So you'll also notice that a lot of our web APIs, not all of them, but a lot of our asynchronous tasks do involve some sort of web API, right? So set timeout, for example, that was a web API. Fetch, that was a web API, right? So we rely a lot on these web APIs for a lot of our asynchronous tasks that we typically do, right? And so remember our two implementations of async programming. We have our promise-based one, what we talked about extensively on Thursday, and then our one example here with our callback-based asynchrony with set timeout. We just pass a function directly in, and it will take care of it. Okay? Any questions so far? All right. So let's explore how callback-based asynchrony ends up working. Right? So the good news is that callbacks-based asynchrony with web APIs like set timeout they largely function the exact same way and kind of in the same process that we saw with event handlers. Right? So for example, let's say I have this one JavaScript, or this one line of JavaScript. I have a JavaScript file. One line is this: set timeout. We want to run that function after 100 milliseconds, right? So again, we start off. This is what our script is. It's just one line. We will add our stack frame for globals, and we call set timeout. And so what set timeout does, remember, set timeout is a web API. And so in the browser, we're asking the browser to say that in 100 milliseconds, we want to run that particular function, fn1, right? And so then what's going to happen is that after 100 milliseconds, the web API is just going to take that callback function and add it to our task queue. So 100 milliseconds in the future, the browser will take that function, add it to the task queue so that it can be executed after that sufficient delay. Any questions so far? Yeah. Yes, that's a very big caveat, right? So a lot of times you think that when I'm writing a set timeout, that function is going to execute in exactly 100 milliseconds. That's not necessarily true. The way it's implemented is that 100 milliseconds in the future, it will be queued up to run next. So if there's some process or there's a lot of code that's currently in our call stack is executing, it might actually be maybe a little bit later, like 105 or something milliseconds. Exactly. Yeah. Good question. So I think the main thing with set timeout, you can kind of think of it as it's an approximation. So we're saying that we want to wait at least 100 milliseconds before this runs, and it's going to run sometime after that. So it's approximate. If you need to be very, very specific, like down to the millisecond, then you might have to program your app in a way that kind of guarantees that nothing else is running so that it can immediately be added onto the call stack. So if like milliseconds really matter, then you might have to like structure your app in a way that allows it to work in that manner. Yes, this is a good question. Yeah. Good question. So yeah, if we are in this case, so are you saying like once this starts executing fn? Good question. So it is executed ultimately by JavaScript. So what happens here, you'll see the web API will add our function call to the task queue, and then eventually that function call gets added to the call stack, and then JavaScript executes it. Mm-hmm. Yeah. Good. Yes. So you would. So in that case, I guess what would happen here, I can kind of draw it out. So if you had some event handler set up, let's say, right, we have something like this. It's document, and then we have some kind of, again, using my, right, let's say FN ID2, right? So what happens is that when you press that button, we will add that function to the task queue to basically run next. So there might be a delay if you press a button while some long operation is running between when you press that button and when it actually runs. It really just depends on how many expensive processes are in the call stack. Yeah. Yeah, so it's kind of an interesting thing to think about, right? Again, very important. So JavaScript it's single threaded, means only one thing can ever execute at a time. So even though there are a lot of user interactions, you may press a lot of buttons, there might be set timeouts running, everything happens in a sequential order, right? Because one thing happens at a time. And we use this queue to keep track of waiting processes, and then we dequeue one at a time and finish executing them. So things like set timeout, even though we write a delay, that's really just a minimum delay. Or like we press a button, there might be a very slight delay between when you press that button and when something actually happens. Yep. Any other questions? Great questions, loving it today. So nice work. Okay. All right. So again, I had here our event loop. Because our global stack frame is idle, we run that function, it gets popped off the stack, and then we continue going. And you notice set timeout as well now is empty because we have run that function. So set timeout is done with what it needed to do. Okay. So now what about fetch? And not just about fetch, but what about kind of all promise-based asynchrony? Because this is callback-based, where the web API adds some functionality to the task queue. So promise-based asynchrony behaves slightly differently. The only difference here is that instead of using the task queue, it uses a separate queue called the microtask queue. So instead of just having one queue, so that one queue is used for callback-based asynchrony, it's used for event handlers, it's used for most of our web APIs. But promise-based asynchrony uses, and all of our promise handling happens with this microtask queue. So just like how we had our task queue here, and again, I apologize because it's a little bit hard to, whoops, I refreshed again. It might be a little bit hard to see it here, but we have a box here for our task queue, and then we have another box here for our micro task queue, right? So these are two separate things. Okay? So then what happens here is whenever we actually kind of set some function to run. So let me kind of write out a very quick example here, right? Let's say we have fetch. Actually, I'm going to use just some other. I'm going to use foo here, and we call this is an async function, and I write dot then here dot then, and then maybe in here I call some other function bar. But just as an example, what will happen is that whenever we run this function, right, we're going to perform some asynchronous task. That might be a fetch, that might be something else. Once it is done executing, bar will be added here to the microtask queue as a task to be completed. So it'll be like this, and then you'd have bar, whatever. So that'll be queued to execute, but it's going to be queued in the second queue, not the first one. And ultimately, the event loop will always prioritize the microtask queue rather than the task queue. So what I mean by that is that if there are things waiting in the microtask queue, it's going to execute those first. Then it will move on to the task queue after that to execute. They're probably wondering why it's designed this way. This is an intentional decision by whoever was designing this and designing the JavaScript runtime, because they believe that based off of how users work, responding to things like network requests, responding to promises should take priority because it's kind of defined by the programmer, so that should take priority there. So I have a question here for you all. What is the order here of execution? So let's say that we run some code. I have these different functions, and I suppose that these should have different names. So I'm going to do that here because I feel like, well, we'll go by the ID because then the animation will get messed up. So if you can imagine, we'll just say this is function 1, function 2, function 3, function 4. So what would be the order of execution here, given this arrangement, assuming our event loop is empty? Any thoughts here? We'll leave it open to. Yeah, I think I saw your hand first. Yeah.
B2, 4, then
Exactly, yes. So we prioritize, or the event loop prioritizes the microtask queue. So our second function first, then our function with ID 4, then function ID 1, then function ID 3. In that order is how it is ultimately executed. Okay. And so lastly, just to discuss with your partner for around 2 minutes, this is our attendance check. There is no paper handout. You can just write in the box. I'd like you to kind of describe this process. So imagine I have this script, and it becomes a JavaScript file. We execute it. We start executing it. What are the steps here that happen in our final runtime diagram? We'll spend a few minutes on this. We'll talk about it, and then we should have some time to answer any midterm questions that you might have. Okay. So attended should be open on Gradescope. You can go ahead and submit. Should be a text box. All right, everyone. Does anyone want to kind of volunteer a description or start us off at least on how this would, what this would look like as we executed our final full JavaScript runtime model? All right, we have a brave volunteer. So we can start us off. What I'll do here is I'll kind of draw out. So I'll draw out. We get some JavaScript file, right, which contains our script. And then from here, what would happen? And if it helps, I'll go back to my old, there we go, slide here. What do we start off with doing? Yep. So first thing that happens, we start off with some global stack frame. Globals, perfect. Exactly, yes. So we will call fetch. And so we can kind of just draw an arrow here. So I'll fill in this part. So we call fetch. And what fetch does is it's going to, again, I'm going to go back to my diagram here. We'll just say fetch is this. And fetch is going to tell the networking service to make a request with this URL, right? So again, we have that URL. We're telling the networking service to go make a request. And so this networking service is going to get started doing that by, so there's going to be an arrow out that's going to start looking. All right, perfect. So then what would happen next? Close. So there's two steps here that will happen first. I guess the first step I'll note is we finished running our program synchronously. So like we ran this, and there's nothing else in our program to run. So real small thing here, I'm just going to write idle. So our global stack frame is now done executing. And then close on task queue. But I want to remind you, so what does fetch, or what, how should I say this? Which type of asynchrony does fetch use? Does it use promise-based or callback-based? Sorry? Yes, sorry. Yes, you're right. Promise-based. And so which task queue would be used for, would it be the task queue or the microtask queue for promise-based asynchrony? Exactly, yes, microtask. So what would end up happening here is sometime in the future, maybe, again, with some expensive operation, we don't know how long the internet takes to run, maybe 200 milliseconds in the future, we will, and I forgot a step here. So before I wrote idle, another thing is that this here is a function, right? So this is some function that we defined, and so we need to add this to the heap. So I'll add like a block. So forgot about that myself. So this is, I'm just going to name it some function. I'm just going to write function here, lines 2 to 4. ID 0 lines 2 to 4. So we add that to our heap, right? And then again, sometime in the future, 200 milliseconds, whatever, later, the networking request, we're going to get some response back from our server. And then the networking service will tell the web API that we have some result in some form, in some, maybe JSON, some other format. And then yes, what will happen is then our web API, because we registered this function in the then function for promises, we are going to add this function. Now that we have the result, we're going to add this function to the microtask queue. So I'll say that I want to run function ID 0 here. We add that to the microtask queue. And then finally, well, our event loop sees that our call stack is currently idle. There's nothing running. And so then the event loop will just take this particular function. So, and we add a call stack frame because we're calling a new function. I'm going to try and keep my color somewhat consistent here. We add a new frame. I don't think those colors are the same, but eyes might be tricking me. So we call function here. And then when we call function, what ends up happening? What do we end up running inside of our function? Let me go back. Exactly. Yeah. So we call console. And incidentally, console is another web API, right? So we have console here. So this function will call console, which will ultimately output something into the result in our browser. And then finally, once we're done, we pop this particular frame off of the stack. Yep. So that was our full, I know that was a lot more. So if you missed some of those, totally fine. As long as you have kind of the general idea. The main thing here I want you to remember is just the fact that we add this to the microtask queue instead of the task queue because it's a promise. And as long as you kind of have that, if you miss some of the intermediate steps, not a problem. Yeah. So close. So fetch, our entire function, our entire function won't finish. Fetch itself just makes the request to the network service. So the actual fetch function will finish once we make the request, but then we will run we'll run that function in our then block. That'll happen after the fact. So it'll log to like our browser tools. Like if you open the browser's console, it'll run there. So for example, I can just open. I have a lot of stuff on my screen here, but if I open up inspect, it's not going to work on here. That's fine. I'll go here. Right, any browser, it's this console right here where it will be printed to. Yep. So the request itself will be completed once we get the result back from the server, but our entire process, will be finished once we run once we log. Yeah. Mm-hmm. Is it finished after it logs? Good question. So in this case, this is very, very specific. I probably wouldn't ask, there wouldn't be a question like that, but if there was, it would be worded, I guess, something like, yeah, I'm honestly not too sure because I think with that one, the wording has to be very precise on the question in order for it to really be asked properly. I'd have to say something like, when does the, I don't know, something like maybe when does a certain function or call stack frame get popped off or something? That would have to be the question, because saying like when does the fetch function actually finish is a little bit ambiguous, right? Because depending on how you define, is just the fetch itself, just the network request finished, or is everything related to that fetch call finished? So yeah, I think I wouldn't ask something like that. A good question. All right. So great questions today, everyone. So again, this is our final built up JavaScript runtime. It includes a call stack, the heap, web APIs, event loop, task queue, and microtask queue. And so you just learned how JavaScript works under the hood and how browsers work and how everything that we've been talking about actually runs in our browser, right? So the runtime essentially underpins everything we do in web programming, right? So this module was really about setting the core foundation of, for example, the DOM, event handlers, higher order functions, asynchrony, all the core pieces that we need. And all of these, you can see how it works in our browser. Throughout the course going forward, we're going to be adding a lot of new different tools, things like React and other tools, building up our toolkit for building much larger, more fun, interactive web applications. However, it's important to note that even though as we add all of these different tools, as we will throughout the semester, past our fundamentals module, in the end, everything that's running, no matter how fancy the tools we're using, is purely just JavaScript in our JavaScript runtime. Right, so this is the foundation of everything that we will see going forward. So in the remaining time, I want to do two things because we have a few minutes. So I want to just real quickly remind you where the details for the midterm are. So that's here on the website. You can press details. And what this will do is this will open up some pieces. So we'll have things about the midterm formatting here. So things like it's 75 minutes, it's on paper, it's multiple choice, some true false, some selectable apply, short answer, etc. Two main things in here that I want to keep in mind, which hopefully will help to reduce your stress. Number one, there will not be code writing. You do not have to write TypeScript code because remembering syntax and writing it out on paper is your hand will be sore afterwards. The graders are not going to be happy. And I don't think that that's a good way. That's not a necessary thing to test because you'll be doing that throughout the semester, right, in assignments. In addition, you will not have to draw memory diagrams at all. So memory diagrams will not be graded. You can use them as a tool if you wish to help, help solve any problems, but you won't be graded on those. And then in here, under midterm content, these are individual, each of these sections essentially correspond to a section on the exam in the same order. So you can see we start off HTML, CSS, CSS box model, some DOM diagramming questions. So there are practice questions and a solution for these. So you know exactly what to expect for that. Some very minor stuff from our first lecture with the client server, TypeScript, some questions, event handling. I linked here the solution to our L04 solution. I think if you understand that, you'll be good for this section. So just as long as you look through that and understand it, you'll be good. Code reading, we also have some practice questions and the solution for those. You can go through these. Again, they range in difficulty. There are some that are quite difficult and are above the scope of they're marked as challenge. So you can think about them. That's harder than what would be on the exam, but it's there just so that you can kind of really test your understanding. So I recommend doing these. And if you have any question on these, you can feel free to ask me or any of the TAs as well. And then finally, something that's very important here, it's written in blue and purple as well for strongly recommend, and it's a hint again here, right? So one of the things that we really want to stress in this class, one of the things you want to get out of it is not just to understand syntax, how things work, coding something up, but also why we do what we do and why we're using certain tools that we do throughout the semester. Because if you go on to build other projects, you work in a company, you do something else, they may use a whole different set of tools. But if you understand why we use a certain classification of tools, if you understand kind of the core concepts, then that is very applicable beyond into anything that you do. So I highly recommend that you look through these questions. You can try in your mind kind of coming up with an answer to these, write these out. That's a hint. This is helpful because these are our core essential questions, right, for our class, for this particular module. So if you understand all of these, that means that you understand pretty much everything that we want you to know in terms of coverage. And then finally, some extra credit questions from today, some of the content today. So if you're still trying to wrap your head around things that we talked about last week, feel free to just study that. This is, after you're done maybe with the midterm and want to look over this again to round out your understanding, feel free to do so. But don't stress over kind of Personally do not like giving new content before a midterm anyway to test on, so you have some time to digest it. So this will be extra credit. And then finally, I've kind of listed here kind of the core key pieces of each of these lectures. So if you just want to, you kind of want to have like a mental map of what's in each lecture, that might be important to know. That is also listed here. Okay. Are there any questions about the midterm or about any particular thing that we've covered so far that you'd like to ask? Yeah. Good question. How many questions? I don't know exactly. I will say though that it matches pretty well to, like, these are each sections. Each section might have like, it varies, like DOM diagramming. There might not be that many because it's just a diagram. Some of the others might have like 5 to 10 each, something like that. But it should be, I will say that the length I feel is pretty similar to last semester. And last semester they had 50 minutes to do it. So I feel like length should be okay. Yeah. Any other questions? All right, remember one last thing. This exam is only, or this midterm is 10% of the grade, right? So do not stress too much about it. It's a good diagnostic tool for us to know where people are. So best of luck. If you have any questions, feel free to ask. I'd be happy to help. We'll see you all on Thursday so you can ace our first midterm. Thank you.